Hello everyone, welcome to this lecture number 38 of the NPTEL course on Riemannian geometry. So, in the previous lecture I introduced normal coordinates, and we saw the geodesic normal coordinates using the exponential map, and we saw that the radial geodesics emanating from P look very simple in these geodesic normal coordinates. Moreover, the Christoffel symbols etc. also all vanish, which means that I mean that is where the word normal comes from, that the Christoffel symbols vanish, and so this as we have seen before makes a lot of calculations much easier to deal with. So, the next goal is to try to prove this local minimization property of geodesics that I have referred to in the previous couple of lectures. The key tool in proving this property is this lemma, which is called the Gauss lemma. So, I want to describe the Gauss lemma in this lecture, and in the next lecture we will prove this local minimization property using the Gauss lemma. Alright, so some notation here. Okay, so for any P in M and any eta positive, we will denote by SP eta tilde to be the set of all tangent vectors in tangent vectors at P whose norm, of course computed with respect to the Riemannian metric, is exactly eta. Okay. So, this is really the sphere of radius eta in the tangent space. Okay. So, here's a definition. So maybe I should also introduce this notation B tilde. So, this is the set of all tangent vectors such that this norm is less than, strictly less than eta. So, now a geodesic ball of radius delta around P is the diffeomorphic image. So, I will denote it by UP delta. So, by definition this is the diffeomorphic image under the exponential map of the corresponding ball in the tangent space. Okay. Where we suppose that the closure is also contained, for convenience we also assume that the closure is contained in a neighborhood on which, so the closure of this ball is contained in a neighborhood on which X is a diffeomorphism. So, we not only want it to be a diffeomorphism on this ball, but we also want it to be a diffeomorphism on a slightly larger open set containing this ball. Okay. Alright, then for eta less than equal to delta, we then set the boundary of this geodesic ball as simply the exponential of this geodesic sphere in the tangent space. Okay. And the remark is that because our exponential is a diffeomorphism defined on a neighborhood containing this ball of radius delta, one can easily prove that that this is in fact the topological boundary and hence the notation makes sense. Okay, that is because a homeomorphism takes the boundary to the boundary, right. So that is why this is going to be the topological boundary of the geodesic ball of radius eta. Okay. Right, so here is the main lemma that I want to prove today. As I said, this is attributed to Gauss. So let UP delta be a geodesic ball of radius delta around P. Okay. Then for any eta less than equal to delta, if you look at the radial vector field that I defined in the previous lecture, that is going to be perpendicular to that is going to be orthogonal to the boundary, okay, boundary of this geodesic ball. Okay, so let's prove this. So let me set up some notation and then I'll draw a picture which will tell you what is really happening here. So let V naught be some point in the sphere of radius eta in the tangent space, and let x naught be the image under the exponential map at P, okay, of V naught. Right, so maybe it's time to draw at least one picture. So let's say this is the tangent space, and let's say your sort of manifold is given by this, okay. So let's say I have a point, I have my origin here and the corresponding point P here, and then V naught is basically this vector. So this is this vector V naught, okay, and this is the sphere S P eta, okay, this is the vector V naught. Now corresponding to that you have this point x naught along, I mean you just trace the geodesic in the direction of V naught. So corresponding to that you have this this point x naught here, and then if you look at the image of this geodesic sphere, that gives you some boundary of the geodesic ball downstairs on M, okay. So now let V of S be some path in the geodesic sphere. So I'll draw that in pink. So let's say V of S is this path here, okay. So corresponding to that I get these tangent vectors V of S, right, and corresponding to that if you look at the image under the exponential map, you will basically get some curve on the geodesic on the boundary of the geodesic ball, and you get this, right. Okay, so let sigma S be the corresponding path in the boundary of the geodesic ball. So that's the image under the exponential map of this V of S, and let x be the derivative at 0. So that derivative at 0 is given by this capital X, and you have the radial vector field del by del rp. So my claim is that this is actually perpendicular. Okay. So the claim is that right. So before that let me also put let gamma be the corresponding geodesic connecting p to x naught. So that is the geodesic given by exponential of t v naught. So note that the radial vector field at the point x naught is precisely the velocity vector, right, up to a factor of eta. Why up to a factor of eta? Because v naught has norm 1, right. So v naught, remember, has norm eta. On the other hand, the radial vector field has norm 1. So this is going to be this divided by eta, right. So it is enough to prove. I want to show that the radial vector field is perpendicular to the boundary of the geodesic sphere, which means I want to show that the radial vector field is perpendicular to all such vectors x. So it is enough to in fact prove that gamma dot of 1 is perpendicular to x. Okay. It is enough to prove that. So let's prove this. All right. So let gamma of s comma t be given by the exponential of t times v of s. Okay. So these are the pink paths. So gamma s is the pink path in the picture. Okay. So this connects p to basically sigma of s, right, because sigma of s is the exponential is the image under the exponential of v of s. So if you put gamma s at 1, that is going to be sigma of s by definition. Okay. So those are the pink paths in the picture. All right. So let f of t, f of s comma t be the inner product of del s gamma with del t gamma. Okay. And my claim 2, so maybe I will call the previous claim as claim 1. My claim 2 is that del f by del t is identically 0. So f is a constant in t. Okay, let me now prove that claim 2 implies claim 1. So then it is enough to actually prove claim 2. Okay. So why is this the case? So note that if you put t equals 0 in your variation capital gamma, then this is just going to be 0 times v of s, which is exponential of 0, which is just p. So gamma s comma 0 at p is p for all s, which means so that just means that if you look at this variation, it basically keeps this point p fixed, right. So that means the variation vector field will actually vanish at that point. So that means that if you compute the variation vector field and sort of plug in t equals 0, then that is going to be 0. Okay. which means that if you calculate f of 0 comma 0, that is going to be 0. Okay. Now let us try to calculate f of 0 comma 1. Okay. So on the other hand, consider the point 0 comma 1. Okay, so there what is del S gamma at the point 0 comma 1? Well, that is just d by ds at s equals 0 of gamma of s comma 1. Okay, but what is gamma of s comma 1? That is just v of s. Okay, if you plug in t equals 1 in the formula for capital gamma, you just get this. But what is by definition the exponential of v of s? That is just sigma of s. So this is the derivative of sigma at 0. By definition that was x, right. We denoted the derivative of sigma at 0 by x. Alright. On the other hand, what is this evaluated at 0 comma 1? Well, that is d by dt at t equals 1 of gamma of 0 comma t, which is what? So gamma of 0 comma t is just the exponential of t times v naught. Okay. But that is precisely this. I mean gamma exponential of t times v naught is the geodesic gamma of t. So this is precisely the derivative of gamma at 1. So that implies that f of s comma t is gamma dot of 1 comma at 0 comma 1 is just this. But then del f by del t being 0 implies that f of 0 comma 0 is the same as f of 0 comma 1, which implies that this comma x is 0 because f of 0 comma 0 was 0. This proves claim 1, right. So now we just have to prove claim 2. Okay, so that is a sort of elementary calculation. So recall that f of s comma t was this. So let us just differentiate in time. Okay, so because it is a metric connection, this is going to be dt del s gamma times del t gamma plus ds gamma times this. Okay, but now for each s, gamma s of t is the exponential of t times v of s. So this is a geodesic. So each of these pink curves that I drew in the previous picture, they are all geodesics, which implies that if you take their velocity vectors and then take the covariant derivative, that is going to be 0. Okay. So this term is going to be 0. Okay. So I am basically just left with this term. So this implies that del f by del t is precisely dt ds gamma dt gamma. Okay. Now by the symmetry lemma, so by the symmetry lemma that we had proved, which was also used in the proof of the first variation formula, you can basically interchange these two. Okay. And you get that this is precisely ds del t gamma times del t gamma. But then again, by using the metric by a sort of calculation that we have done often enough, this is just half d by ds of del t gamma squared. Okay, now again each gamma s is a geodesic, which means that that del t gamma squared is basically just equal to the norm of the initial velocity vector, the norm squared of the initial velocity vector. But what is gamma s dot of 0? This is just d by dt at t equals 0. Gamma s is just given by exponential of t times Vs, okay, which by the definition of by the exponential map, this was part of the proposition that we had shown, is precisely just V of s norm squared, because this initial velocity vector of this geodesic is precisely V of s, right. Sorry, not this derivative is precisely just V of s. But now V of s was a curve in this sphere in the tangent space, so this is always eta squared, okay. So in other words, this is a constant in S, which implies that d by ds of the norm squared of this is d by ds of this constant eta squared, which is 0. So this proves that del f by del t is 0, okay. So that completes the proof of claim 2 and hence the proof of Gauss lemma. All right, so maybe I'll end this this lecture with a nice consequence of the Gauss lemma, and then we'll take the discussion forward next time. So let up comma delta be a geodesic ball with geodesic normal coordinates then as before. So let Rp and del by del Rp be as before. Then on this up minus p, again we are looking at points away from p, because del by del Rp is not defined at p, right. So away from the point p, we have this beautiful relation that if you take the gradient of Rp, let me remind you of what the definition of a gradient was. It's been a long time since we defined the gradient, but the claim is that the gradient is just del by del Rp, okay, at any point x here. So let me remind you of the definition. So recall for any function f on some open neighborhood u, the gradient at x is characterized by the following property. So it is basically just defined to be the sharp of df at x, okay. So in other words, equivalently for all tangent vectors in the tangent space at x, we have the following, that that V, the derivative of f in the with respect to V is precisely given by the inner product of the gradient f with V. Okay, that's the definition of the sharp operator, because this is precisely df applied to V. Okay. So in other words, the gradient is basically characterized by this property. Okay. So now let us try to prove the corollary. Okay, so what is the goal? Using this sort of characterization in the blue box, the goal is to show that for all local vector fields, right, I want to show that x of Rp is the same as del by del Rp times x, right, because then del by del Rp will be precisely the gradient of so then this would imply that this is just the gradient of Rp. Okay. So it's enough to prove this equality in the box. Okay. All right. So so by the Gauss lemma, given this x, we can decompose it into a component along this radial vector field plus x prime, where x prime is perpendicular to del by del Rp. That is exactly the statement of the Gauss lemma, right, that if you take so x prime is perpendicular to this, and x prime at any x lies in the tangent space to the corresponding geodesic ball. So suppose right, so maybe let me let me erase all this. Let us be more specific. So let us prove the claim at some point q given by exponential of t naught times v naught, right, where norm v naught is 1 and t naught is simply the radial distance to q. Okay. So then Gauss lemma implies you can write this as a times del by del Rp plus x prime, where x prime is perpendicular to del by del Rp and x prime is tangential to these geodesic spheres for all eta less than equal to epsilon, right. Okay, so then this implies that x prime on the applied to this radial distance function, because the radial distance function is a constant eta on the boundary of the geodesic ball of radius eta, right. So if you differentiate it in the tangential direction, you are going to get 0. So that means that x of Rp is precisely a times del Rp by del Rp, which we have seen is just 1. So this is simply a, right. Okay. On the other hand, what is del by del Rp inner product with x, well that is that's just A times the norm squared of this plus x prime inner product with del by del rp. But this is 0 because x prime by Gauss lemma is orthogonal to del by del rp, and this guy is equal to 1 by one of the things that we proved in the previous lecture. So this entire thing is A, but we have seen A is just x of rp. So that means x of rp is given by this. So this proves the claim, and this was for all choices of x. X was completely arbitrary. So this proves the claim, and hence that the gradient of rp is this. So in particular, let me maybe end with the following remark, that this basically means that the gradient of rp squared is also identically 1. Okay. Alright, so next time we are going to use this in order to prove the local minimization property. Okay, so that's it for this lecture. Thanks for your attention, and I will see you in the next lecture. Thank you.